Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk about categories and give you the definition of them, as well as some basic examples and simple properties of them. So category is essentially an environment which abstracts the common principles between different branches of mathematics. And it's the environment which allows us to use the functoriality argument that we saw in the previous video to make the invariant base number theorem work. Okay, so let's give the definition of a category. Okay, so a category, often denoted with some script symbol like the script C here, it concerns three pieces of data. So the first one is a collection of objects, so that's object C. Okay, the elements of this are called objects. That's the first piece of data. The second piece of data is for each pair of these objects, so A and B are elements of this collection, we're going to consider a set called a Hom set, C from A to B. So we should think of these as the morphisms from A to B, kind of like structure preserving morphisms. Okay, so as some notation, this is just a set, so we can always write F is an element of this set. But to remind us of how we often use them, we might use this sort of notation here. F over this arrow, A to B. So that just means F is an element of this Hom set. Okay, and the third piece of data is how we can combine Homs together. Okay, this is a set of Homs, okay, or a set of morphisms, and so that's the composition law. And that occurs in this context here. Suppose we're given three objects, A, B, and C, okay? And you're given a Hom from A to B and a Hom from B to C, then you can combine them to get a Hom from A to C. Okay, so let's see how that works and the notation for it. Suppose you've got something from A to B, so an element of this Hom set. Okay, let's call it G. And you've got an element of this Hom set from B to C. Let's call it F. Then you've got something from in this Hom set from A to C. Okay, so we're going to write it in the usual composition of functions notation. You do G first and F. So G is on the right and F is on the left. Okay, so given a pair like this, F is in here, comma G is in here, you get a new element which is in this Hom set. So there's three pieces of data and they have to satisfy certain axioms. Okay, and I hope you can guess they're fairly natural. The first one is that the composition has to be associative. So if instead of just composing two of them, you have a third function that you can compose with, say H, then it doesn't matter whether you compose F and G first and then compose that with H, or you do compose the G and H first and then left compose with F. Okay, that's the usual associative law that we see in lots of branches of mathematics. The other thing is that for each object A inside this category C, we're going to have a special function in the Hom set from A to A, C from A to A. We denote it with one A. It's called the identity on A. And basically it behaves like the identity. Okay, but it behaves like the identity given this data. So how can we make it sense of the identity given this data? Well, the key point is when you compose the identity with any morphism, it doesn't change the morphism, provided of course you can compose. So 1A composed with F is equal to F, and G composed with 1A is equal to G, provided that the left-hand sides are defined. Okay, so at the end of the day, this category, you can think of it as a very, very algebraic object, and it's quite similar to other algebraic objects that you might have seen before. Okay, so essentially, you've got a partial composition. Okay, you can compose morphisms, but not any two morphisms. It's only when they line up correctly. So for example here, this one here has to go from A to B, and this one from B to C. It's only in this situation that you can compose these Homs to get a new Hom. Okay, so that's the first thing. It has a partially defined composition law, so to speak. And when it is defined, is given by the data of the objects. Okay. The next thing is that instead of having a single identity that you see in a group, you have many identities, one for each object. Okay, so these identities, they're similar to what you see in a group. When you multiply with that, it doesn't change anything. Okay, and that's the definition of a category. Okay, so let's move on to some basic examples that are very common in mathematics. Okay, so I'm going to give 1, 2, 3, 4 examples in this first lot, which are fairly common. Okay, and in all these examples, you're going to have to give these three pieces of data, And the composition law will always be composition of functions. So the HOMs will always turn out to be actual functions between sets, and the composition law will be just composing functions. And since when you compose functions, that composition is associative, this axiom here will always hold. The other thing that we'll have is that the identities on the objects are just the identities on those sets. So since they're identities, when you compose with an identity map, of course, it doesn't change the map. Okay, so this second axiom will hold as well. Okay, so let's see what they are. So the first one is the category of sets, and it's denoted like this. See, of course, we write set and we put an underline to emphasize that it's a category. What's the data we need to give? We need to give a collection, okay? So a collection of objects. So what are the objects? So the objects are sets. So it's the collection of all sets. Okay, that's the first piece of data. And then you'd have to say, well, given any two objects, so given any two sets A and B, what are the HOMs from A to B? Well, that's going to just be the set of all functions from A to B. Okay, and that, of course, is just a set. And when you have that, of course, you can just use the usual composition of functions to give you a composition like this. And as I've mentioned before, these two axioms automatically hold. So that makes it a category, okay, and a very important one. Okay, so let's look at another example. Okay, so this is the category of groups. Okay, so again, we have to give the data of a collection, and that collection is just the collection of all groups. So an object in this category is just a group. Okay, and now given two elements of this collection, so two objects, so two groups A and B, we have to say, what are the HOMs from A to B? Okay, what is that HOM set, that set of HOMs? Okay, well, they're just the group homomorphisms from A to B. Okay, and of course we know that when you compose these HOMs as functions, okay, if they're group homomorphisms, the composite of group homomorphism is a group homomorphism. Okay, similarly, the identity gives you a group homomorphism. So in fact, that's a well-defined element inside these HOM sets. Okay, and we can use these to define the identity elements here. So this gives you the category of groups. Okay, so let's look at a slightly different example, a non-algebraic example, and this is the category of topological spaces. Okay, so here, what are the objects? The objects are topological spaces. Okay, and if you're given two topological spaces, you want to say, well, what are the HOM sets? Okay, so what are the HOMs from one topological space to the other? They're just the continuous maps. Okay, and the final example I want to give you actually is a collection of examples, one for every ring R. It's going to be R mod, the category of left R modules. So as the name suggests in all of these, I guess there should be an underline here. We often name a category after the objects, okay? So here, the R modules are the objects, the left R modules, that's why this is the category of left R modules. And then you have to say, what are the HOM sets? Okay, the HOM sets are just the module homomorphisms. So all the HOM set from a module R module A to R module B is just the module homomorphisms, or the R linear maps from A to B. Okay, and they give you 4 examples of categories. Okay, so I hope you can see how this notion, right, it appears in lots of different branches of mathematics, and it encodes common themes that you see in all these cases. Okay, in each case we have some special sets. Okay, well, sometimes they're just sets. Okay, but sometimes they're sets with extra data, like the groups here, or sets with extra data, like a topology, or sets with extra data of both an abelian group and also a scalar multiplication by elements of R, which satisfy certain properties. And then there are special functions between them, structure preserving maps. Okay, so what we've done is we've abstracted all those common notions, and when you do that, that gives you the notion of a category. Okay, so let's move on to a slightly more abstract example. Okay, and in this abstract example here, it's called the opposite category. We're going to start with the category C here, and we're going to construct from that what's called the opposite category. Now, if you've seen the notion of a group and the opposite group, this should be quite easy to understand because it's very, very similar to what you have there. Okay, so in the opposite group, basically the elements are the same. You just change the multiplication by swapping the order that you put things in. Okay. Okay, so what are we going to do here? Okay, so in this opposite category, we need a collection of objects, a collection of HOM sets, and also composition law. Okay, so what are the objects? The objects don't change in this case. Okay, the objects of the opposite category C opposite is just the objects of the original category C. what are the Hom sets? Okay, the Hom sets actually don't change that much, but just to make things a little bit clearer, I'm going to replace each of them with a copy of the Hom sets inside C. Okay, and so what's going to happen? So the opposite category, the Homs from A to B, you're going to actually get them by looking at the Homs from B to A in the original category. So we've swapped the A and B so that you're looking at the Homs from B to A now. So for each one, we're going to pick a copy. So I'm just going to write it as an F opposite to make it a new thing, to make it clearer to mark out whether we're looking at Homs inside this opposite category or inside the original category. Okay, that's the only reason why I did that, but I guess I could set it up differently. Okay, so the final piece of data is, of course, how you compose Homs. Okay, so suppose you have two composable Homs in the opposite category. Okay, so say F opposite goes from A to B, and G opposite goes from B to C. Okay, so we need something that goes from A to C. So that will be F opposite composed with G opposite, like that. Okay, so what is that? So let's give the definition of that. Of course, it has to be something that's a Hom in the opposite category from A to C, which means it's a Hom in the original category from C to A. Okay, so we want something, so the bottom line here will be in C, and we want something from C to A in the original category here. Let's see what that is. Okay, so let's look and see where these come from. Okay, so the G opposite, that's from B to C in the opposite category, so that comes from a map from C to B in the original category. Okay, so the arrow goes backwards here. This F opposite is a map from a Hom from B to A in the original category. So since these are in a category, you can compose them in that category C to do, well, you do G first and then F. Okay, you do G first and then F. So now you have a Hom from C to A in the original category, and so the copy of this that's inside the opposite category gives you a Hom from A to C. So what we see here now is that we can define this composition here of F opposite composed with G opposite as G composed with F in the original category, and you look at the corresponding copy inside the opposite category. And in this case here, you have to check a little bit more. Okay, you actually have to check the composition is associative, and if you've seen how the opposite group is also a group, so that the multiplication is still associative, the same proof will show that the composition here is associative. The other thing that you need to do is you need to check what is the identity in this case. Okay, and does the second axiom hold? Okay, well, in this case here, well, you have an identity from A to A in this C, so that gives you a corresponding element in the opposite category, a Hom from this A to A, but it's still from A to A. And it's quite easy to see that basically this one will give you the same identity. So it will satisfy these two, because essentially what have you done? When you pass to the opposite category, what's the big change? When you do the composition here you do G composed F, but here you've twisted them around. So F composed G is essentially corresponding to the product in the other direction. So when you look at the op, okay, of these things, okay, you basically swap the order in which they come. Okay, so if you look at the opposite of this FG, you swap the order, so you can take the opposite copies of these two morphisms on both sides, so you get F opposite here, and this will be F opposite on the left composed with 1A opposite on the right. Okay, so that gives you this equation, and then the opposite of this will give you this equation. So in this case, the identity axiom also holds. There's another abstract way of constructing categories from other categories that's very important, and that's known as the product category. So suppose you're given two categories, C and C prime. We can construct the product category C cross C prime as follows. So basically, what are the objects? That's what we need to define first. They're just pairs of objects. A prime, where A is in the first category C, and A prime is in the second category C prime. What about Homs? Okay, so suppose now we're given two such objects, so two such pairs, A prime and B prime. And in this product category, we want to see what is the Hom set from here to here. Basically, they're just pairs of Homs. Okay, so firstly, there's F, a Hom from A to B, from this A to this B, and then there's a Hom F prime from A prime to B prime, from A prime to B prime. So this is a Hom inside C, and this is a Hom inside C prime. Okay, so they're just pairs of Homs. And then the last piece of data we need to define a category is the composition of these Homs. Okay, so suppose we're given two of them, FF prime and another one GG prime. Okay, how do we compose them? We need a pair of Homs like this. Okay, and all it is you compose G with F and G prime with F prime, like that, and that gives you a new pair which defines a Hom from the composite. So that's the composite Hom. Okay, and it's quite easy to see that, of course, since composition is associative here in C and also in C prime, you get associativity inside here as well. And if you want to know, well, what's the identity on A comma B, or A comma A prime rather, so if you have A prime here and A prime, okay, you want a Hom from here to here, which is the identity. Of course, you just have the identity on A and the identity on A prime, and that gives you the identity. And it's quite easy to check the axioms here, and that gives you the product category, which is a very important way of constructing a new category from two old ones. Okay, so I want to finish off this video by telling you about some notions which are common to all categories. So one thing that was rather interesting in that video on the invariant base number theorem is that you have a notion of isomorphism for R modules, and this got translated into a notion of isomorphism in vector spaces. Okay, and one of the reasons why you can do this is the fact that the notion of isomorphism you can express purely categorically, and hence in all these different varieties, and also swap between them eventually when we talk about functoriality. Okay, so let's see how we can express the notion of isomorphism in any category we like. Okay, not just for R modules. Okay, so what is an isomorphism? It's a particular type of Hom. By the way, these Homs are also called morphisms. So it's a Hom. So let's say you've got F is a Hom from A to B. Okay, we say it's an isomorphism when there's basically an inverse Hom. Okay, so that means an F inverse which goes from B to A, such that, well, once you have a Hom from B to A, you can compose them as F inverse F that goes from A to A, and you want that to be that identity on A. Okay. So by the way, it's quite easy to show that the identity on A is uniquely defined. Okay, and similarly, F composed F inverse is the identity on B. Okay, so let's just see what this notion tells us in the various examples that we saw before. So inside the category of sets, okay, so the Homs here are just set functions, and of course this definition here is precisely just the definition for the usual inverse function. Okay, so to be an isomorphism just means you have an inverse function. In other words, it's an invertible function or a bijection. Okay, so that's an isomorphism in the category of sets. It's just a bijection. What about in the category of R modules? Here you just have an inverse module homomorphism, so that's just the notion of a module isomorphism. And finally, in the category of topological spaces, what does this definition give you? To be an isomorphism just means you have an inverse continuous map. So that means that that Hom is actually a homeomorphism. Okay, so that's the notion of isomorphism in topological spaces. So it's quite nice that to express this notion of an isomorphism, you just need the data of a category. Okay, you just need to know how to compose morphisms as long as they're composable, and this condition sets it up so that it all works out correctly. And also you need the notion of an identity. Okay, that's all you need. Once you have that, you can define an isomorphism. Okay, so I want to give you some more notions which are common to all categories. Okay, so the first one is the notion of an initial object. Okay, so let's suppose you have an object 0 inside object of C. So 0 is just the notation for something. Okay, we call it an initial object if basically there's a unique map coming out of it to anything else. So for any other object A inside C. By the way, I should just remark some notation here. Often, what does this mean? A, an element of C. Really, this is just shorthand for A is an object of C. Sometimes we leave out this obj here. Okay, so A is an object of C. Given any such object of C, there is a unique Hom from that 0 to that A. So you can change this A to whatever you like. There's always just one unique Hom from 0 to that A. This is rather symmetric. Of course, you might want to swap the roles of A and 0, and if you do, you get the notion of what's called a terminal object. So 0 is a terminal object if basically everything maps to that 0, and there's a unique map to that 0. Okay, hence a terminal object. Initial, anything maps from that object and in a unique way. And then there are some times when you have something which is both initial and terminal, and that's called a null object. Okay, a null object is just one which is both initial and terminal. Okay, so let's see examples of this notion. Okay, so suppose we're in the category of sets or in the category of topological spaces. They will actually have the same initial object. The initial object here is just the empty set. Okay, the empty set, you can always map it to any set. Okay, and there's only one map from the empty set to that set. Okay, you have to say where all the elements go, but there are no elements, so there's nothing to define in that function. Okay, and that map, of course, is also continuous. Okay, so in that case, you'll find that it's also the initial object in the category of topological spaces. Okay, now let's look at the final objects in these two categories as well. So here we're going to look at point. So what does point mean? It's just a single element set. Okay, so it's not any particular set or topological space. It's any one which just has one element in it. Okay, so we'll use PT to denote it as a point. So thinking of it geometrically, it is a point. Okay, so given any set, of course, you can always map it in a unique way to a one element set. You send everything to that one element. There's no other possibility for what that is, and that map always exists. And that map will be continuous if that set that you're mapping from is a topological space. Okay, so map to a constant map to a single point is always going to be continuous. So this is the final object in the category of sets and also the category of topological spaces. Okay, so note here, the initial object and the final object are actually quite different. And what's an example of a null object? So we can see here that we don't have a null object yet. We have an initial and a final. In fact, in these categories, you don't have null objects. But in the category of R modules, you do have a null object, and that's the 0 module. Okay, so you always have a 0 module. It doesn't matter what ring R you work with. And of course, given a 0 module, you can map it to the 0 inside any module, and that's the unique module homomorphism that you have out of this 0. Okay, and also given any module, you can always map everything down to that 0 element, and that's the unique R linear map from a module to 0. Okay, so it is both an initial object and a terminal object, and hence a null object. Okay, so I want to say some interesting properties that we can say about these initial and terminal objects. Okay, so the first thing is that, and this also brings in the notion of the opposite category. So an object Z0 inside category C is initial if and only if it's terminal inside the opposite category. Okay, so this working with the opposite category allows you to talk about what's called duality. So duality is what happens when you flip the direction of arrows. Okay, so often you'll find results which occur in dual pairs, okay, or notions that occur in dual pairs. And the initial and terminal are examples of notions which occur in dual pairs. Okay, so let's just see how that happens. Okay, so of course here, when you look at the condition here, what do we do to get from one to the other? Well, one way to say it is we just flip the order of the arrows. Okay, so here it's in both cases the quantifiers is for all objects A inside C. Okay, but here one goes from 0 to A and one goes from A to 0. So we swap the order of the direction of the arrows here. Okay, so let's have a look and see how this works. Okay, so suppose you're considering the notion of initial. Okay, inside C. Inside C, to be initial means that there's always a unique map from 0 to any A. Okay, and you're looking at that. But of course, when you're inside the opposite category, what does this correspond to? So remember, the hom sets really correspond, but you have to flip the direction of the arrows. Okay, so the hom from 0 to A inside C are precisely the identified with the homs in the opposite category from A to 0, from A to 0. Okay, so if there's a unique hom from 0 to A in C, then there's a unique hom from A to 0 inside the opposite category. So that means that you get a terminal object inside the opposite category. Okay, so that's basically the proof of A. Okay, and that's one way to say things about dual notions, okay, to work with this opposite category, okay. If you know there are certain facts which are true for all categories, okay, then often when you apply it to the opposite category, you get a new result, okay. So if you know something about initial categories, like this fact that I'm going to prove here, okay, and it's true for all categories, then applying it to the opposite category will tell you a corresponding result for terminal objects. Okay, so let's look at part B, which is an interesting result here. Any initial object is actually unique up to unique isomorphism. Okay, so this needs a bit of unraveling what it means. Okay, also if you apply this to the opposite category, this will show you that any terminal object is unique up to unique isomorphism. Okay, well, let's have a look at this example here. Okay, so here you have terminal object, it's just one single element set or one single element topological space. Well, there are lots of them, okay? You can have a single element topological space here, and you have another point here, okay? Two separate points, okay? So they're different. So they're not unique in the sense that they have to be the same, but they're unique in the sense that firstly, they're isomorphic. Okay, so 2 points are of course isomorphic as either sets or topological spaces, but also it's more precise than that. Not only are they isomorphism, but there's only one isomorphism from one of these points to the other one, and also its inverse is the unique isomorphism the way back. Okay, so of course if you're given 2 points, okay, how many maps do you have between them? There's only one map between them, okay, and that's the isomorphism between them. Okay, so that's what it means to be unique up to unique isomorphism. Okay, and the proof of this is fairly easy. Okay, so suppose we have two initial objects. We'll call them 0 and 0 prime. Here's 0 and here's 0 prime. Okay, and what we're going to use is you're going to use the fact that 0 is initial and 0 prime is initial to say that we have lots of maps floating around, and of course the maps that I'm going to write down here, they're all uniquely determined by the fact that 0 and 0 prime are initial. Okay, so firstly, 0 is initial, so it will map to both these two elements in a unique way. It will map to 0 prime in a unique way, say via f, and it will map to itself in a unique way. Of course, there exists a map from here to here, which is the identity on 0, so it has to be that one. That's the unique map that way. Okay. Now we use the fact that 0 prime is initial. Okay, so there's a unique map going to this 0. We'll call it G, and there's also a unique map from this 0 prime back to itself. Of course, we know that one of them is the identity on 0 prime, so that has to be that unique map. Okay, so I've defined all the maps there just by using the fact that 0 and 0 prime are initial. What do we need to show now? To prove this proposition, okay, we need to show that f and g are isomorphisms, and then we're done. Okay, so once they're isomorphic, then not only are 0 and 0 prime isomorphic, okay, so that just means there's an isomorphism between them, but that isomorphism is unique because actually there's only one Hom from here to here, right, and that's f, and similarly there's only one Hom from 0 prime to 0, that's g. Okay, so that's all we need to do, show that that's a f is an isomorphism, and as it turns out g will be the inverse isomorphism. Okay, so let's see how that is. So let's suppose we do f and then g, so we go f and then g, so that gives you a Hom from 0 to 0. But this is an initial object, so there's only one Hom from 0 to 0. That's this one here. So this G composed f has to equal the identity on 0. And similarly, there's only one Hom from 0 prime back to 0 prime. That's the identity on 0 prime. So if you go G first and then f, right, that has to be that unique Hom. Okay, so fg is 1, 0 prime. And these two equations show you, just using the definition of isomorphism, that f and g are inverse isomorphisms. And that way we've proved that initial objects in this category are unique up to unique isomorphism, and applying this result to the opposite category and using part A shows that also any terminal object is unique up to unique isomorphism. I hope you enjoyed this adventure in pure mathematics.